At this point, let's say we want to investigate the behavior of the AG25 foil at 100,000 Reynolds number. So this is this curve here with the little squares. So we'll start by hiding all polars except this one. So I'll select it and display it. Here it is. And I'd like to understand, for instance, the behavior in this range of AOA where we can see a drop in the lift coefficient. Now we know that this is probably due to Storm effect, which we can investigate in the foil view. So this analysis, this polar has been selected and will generate now the operating points which we did not generate earlier, and this is done by activating this checkbox here, store operating points. And I'll create them from 0 to 10 degrees and then from 0 to -6 degrees. Let's go. And let's have a look at the boundary layer. So at -5.75 degrees we have separation of the flow on the inner surface, lower surface, and this explains why X-foil had difficulties converging at -6 degrees. For large separations, X-foil finds it a bit more difficult to find a solution to the panel method. Now let's have a look at the behavior of the boundary layer as we go from 10 degrees to -5.7 degrees. You can see that here we have a sort of bump on the graph. This is the upper surface, and this is the pressure on the upper surface, and this is the pressure on the lower surface. This shows that we have local recirculation of the air. The air goes in a loop at this point of the foil, and this creates the separation between the surface and the laminar flow. We will be laminar here, turbulent here. The turbulence is due to the viscosity of the air and its friction against the upper surface of the foil. And this separation changes with AOA. So if we now try to go down the AOAs, reducing the angle of attack, we see this separation bubble moving backwards until it's almost at the trailing edge, and this is the range where we will expect minimal drag. So for an angle of attack of 1.25 down to something like maybe -1 degree, we don't have any separation except at the rear of the foil, and we should be getting minimal drag. And as we go down the AOAs, we see the separation occurring on the inner surface. Okay. Now what I would like to do is investigate the impact on the performance of a flap, sorry. So let's set a flap here on this foil, a trailing edge flap, let's say 7 degrees down, and locate the hinge at 70% from the leading edge. And I'll change name to 7 degrees, or flap down 7 degrees, so as not to overwrite the original foil. Flap down 7 degrees. Here we are at last. Okay, and we can see the flap here on the trailing edge, and I'll create the same with an upwards flap deflection using this same foil here, So -7, okay, and I'll change the name to flap up. Here we are. I'll create one polar object for each at 100,000 Reynolds number with unchanged transition parameters. Here we are. For the flap up foil and for the flap down foil, same thing. And now let's run the analysis. From 0 to -6, then from 0 to 10. Okay. And the same for the other flap, the other foil with the flap up. Oops. Now let's switch to the polar graph again and see what difference it makes. Well, I'll change the color of the flap down polar because it's really confusing with the one of the non-flap foil. So I'll switch from orange to, let's say, something like green, bright green, and a thick width. Okay. So when the flap is down, what do we see? We have, compared to this reference polar here, we have increased lift, but we also have increased drag. This is the kind of behavior we should expect when setting the flap down. And on the opposite, when we set the flap up, we get lesser lift, but not so much less drag. And this is the cause of inverse yaw when flying those large sailplanes. Okay, so this seems to be consistent up to now. At the next stage, what I'd like to do is try to show the inverse design of foils using X-foil.